How does the implication of various pulley systems increase force on a system? To fully understand this question, we need to know what work is. Work is force times distance. In our problem, we have a constant force, which is my mass times acceleration, which in this problem is tension. So if we want to increase work, we have to increase the distance we pull. To solve for force, we simply solve for T2 in our equation.
Hi, today we're going to be talking about the various mechanical advantages of pulley systems using the key equation of work, which is force times distance. Today we're going to be using a lot of pulleys, so what we need to understand is what a pulley is. And a pulley is a simple machine that simply redirects the force. So today we're going to be doing a 3-to-1 pulley system and a 9-to-1 pulley system and compare the forces. All right, so we just set up a 3-to-1 pulley and I'm going to explain it to you real quick. So we're going to start off with our base anchor. We're going to follow up on the top rope and we have a set distance here. It's going to go through our static anchor, through our first pulley, which is a traveling pulley, which is going to multiply the tension all the way back to a redirect to where I'm pulling. So when I hang here, I can hang about 180, 170 pounds. And we have 3 tensions, so 1, 2, 3 tensions here, and that's gonna give us the 3-to-1 pulley. And we'll show the math now. Here we have a 3-to-1 pulley visualized. We have our initial measurement D1, the top length, and the bottom length D2. When I pull tension 1, the tension follows through the line and we gain 3 T1s. So 3 T1 equals T2. And by putting in my weights, 555 newtons, we ended up getting 2,266 newtons. With such a small error of 7.4%, we know that we have nearly an ideal 3-to-1 pulley system. All right, so now we just set up a 9-to-1 pulley and we're gonna do the same thing. I'm gonna follow you through the forces. So I'm gonna pull, again, my 77 kilograms. Tension is gonna go through here. We got another traveling pulley. So that means the force is gonna get multiplied. So right now we have 2 tension, go back through the first pulley and back to our anchor. And that's essentially a 3-to-1 like we already saw. So 3 forces here. So now we have 3 tension here and we're gonna follow again through another 3-to-1 pulley. So 3 tension here gets doubled. So we have 6 tension, go back through and another 3 tension. So now we're gonna have 9-to-1 total. So when I hang here, we'll see, it's gotta get back up. I can pull a ton of rope, actually 9 times the distance here, then the distance is gonna move up here. So I can multiply my work with the pulley. Here we have a 9-to-1 pulley visualized on paper. While it looks complicated, it's much simpler than you think. It's simply a 3-to-1 pulley on a 3-to-1 pulley. So we'll follow the tensions just like before. We have 1 T1, 2 T1, 3 T1. That sums up to 3 T1. So we're gonna cover up the first 3-to-1 pulley and follow it just like we did before. 3 T1, 6 T1, 9 T1, which is all equivalent to T2. If we put in the tension I put on the line, 755 newtons, we end up with a T2 of 6,798 newtons. And we can prove this is a 9-to-1 pulley by taking the ratio of the change in D1 over the change in D2, which gives us 9.74, which is nearly a 9-to-1 pulley with an error of 8.2%. So after looking at the calculations, there was a very small margin of error, but we're going to talk about where that must be coming from. So the biggest margin of error that we expected was from mismeasuring the length of each rope. The second huge error could be coming from the friction, which is going to be subtracting the force, which is going to impact the amount of work done on the pulley. The last margin of error, and it should be small, is that our pulleys are imperfect or not ideal. And we're losing force with each turn of the pulley.